Hello, I'm Paolo Marzioli
And I'm Lorenzo Frezza.
from Sapienza University of Rome, and welcome to the third video tutorial on the SDR Play course in Understanding Radio Communications using SDRs. This video is linked to Lecture 7 of our course, Receiving Data from a Dummy Transmitter Part 1. During Lecture 7 and Lecture 8 of the course, the students will learn to receive, demodulate and decode some data that you will transmit through an inexpensive radio transmitter. These students will use nothing more than an SDR Play RSP radio receiver and a GNU Radio Companion for the reception and interpretation of the data. During Lecture 7, the students will start from the empty canvas on GNU Radio Companion until arriving to the demodulation of the dummy transmitter data. While in Lecture 8, we will arrive finally to the interpretation of all the data. I immediately hand over to Lorenzo that will show you the content of Lecture 7.
Thank you, Paolo. The first thing we're going to do is connect our transmitter to the Arduino and the Arduino to the computer in order to generate the signal that we need for the lecture. We are going to follow the guide that we provide in the slides to connect the transmitter to the Arduino. We connect the ground pin to the ground pin of the Arduino, the power to 5 volts since we're using an Arduino Uno, and then slave input to D11, slave output to D12, chip select to D10, clock to D13, and interrupt to D2. We can then connect the Arduino USB to the computer. First thing we are going to do is make sure that the correct script is running on the Arduino connected to the transmitter. In this case, we chose to transmit at 423 MHz with a 1200 baud. Let's upload the script to the Arduino. And then we can switch on the RSP and we see a signal at around 423 MHz, actually a little bit less, which is our transmitter. You see that if we change the configuration on the Arduino file, for example, let's increase the baud rate. We see that the signal changes. In this case, the time of transmission became a little bit shorter because the baud rate is doubled. Okay, let's switch back to 1200 baud for the moment. And let's try to receive the signal on GNU Radio instead of SDR Uno. So let's stop and close SDR Uno. And let's remove the old script and start over. So we want to add an RSP1A source block. This is the RSP we are using. And let's connect it straight to a Qt GUI sync to see if we are actually able to receive the signal. The frequency, we can set it directly to 432.97 MHz. Let's press play. And yeah, we can see the signal in the center. If we increase the FFT size and zoom in on our signal, we see that it is around 10 kHz on one side and around 10 kHz on the other, so around 20 kHz in size. So we want to limit the bandwidth of the signal to this 20 kHz of signal, and we want to ignore any frequency which is above the 10 kHz on one side. By using a low-pass filter of cutoff frequency 10 kHz, any frequency above 10 kHz and below minus 10 kHz will be attenuated. So let's add a low-pass filter by searching for it on GNU Radio. And let's set the cutoff frequency to 10 kHz. Transition width could be a tenth of that, 1 kHz. And let's press play. Perfect, now we have our signal, more or less in the middle of our bandwidth. If we have some uncertainty in the frequency, we can increase the bandwidth. For now, let's try to set it to keep it at 10 kHz of cutoff frequency, so 20 kHz of bandwidth. And we still have all this bandwidth unused, which we don't want. So we can decimate the signal. I can do a decimation of 50, which means that from 2 MHz we'll get down to 20 kHz, exactly what we want. We can use a variable for this. Let's use a variable called DEC, which we will create. So let's look for variable. Let's call it DEC and give it a value of 50. Then, of course, on the Qt GUI sync, the bandwidth, which is the sampling rate, we'll set it to sampling rate divided by DEC, because the decimation divides the sampling rate in the input by its value. Let's press play. And now we have, you see the signal, which sits comfortably in our bandwidth. We actually see that the signal is not centered. It is slightly on the right. It is around 2 kHz on the right. So let's fix the frequency so that we tune exactly on the signal by moving 2 kHz on the right. Let's press play. And there you go. Now we have our signal, which is around 20 kHz in size, inside a low pass filter, and around only 10 kHz of extra bandwidth on each side. Now we have isolated our signal. We could make the low pass filter a little bit tighter to go around our signal, but this is enough. Let's try to demodulate the signal. We know that this signal is FM modulated, so we can use an FM demodulation block. A generic block that we can use for this is actually called quadrature demod. The quadrature demodulation is a kind of FM demodulation which can be used to demodulate digital signals. Actually, let's use the Qt GUI sync to actually see the output of the quadrature demod. We see that the output of the quadrature demod is a real signal. This is because if you demodulate a complex FM signal, you get a real output, which usually is audio, as we saw before when we are trying to receive the FM radio. But in this case, the real signal will be our data signals, which are not complex but are real. Let's switch the Qt GUI sync to float and connect it to the quadrature demod. If we open up the settings, we see it has the parameter of the gain, which is used when demodulating the signal. We actually look at the documentation to see actually what the gain does. But in this case, we can just set it to 1. It will be enough. In most cases, 1 is appropriate. Let's press play. And at the moment, we are watching the frequency domain, but since we are demodulating the signal and we are getting a real value, we actually want to look at the time domain, because this doesn't contain any useful frequency domain data. So let's go to the time domain, and you can see that we are actually demodulating the correct signal. We see a square wave, which means that the signal is correctly demodulated. And usually when the signal is high, this represents a 1, and when the signal is low, it represents a 0. This is not always the case. Sometimes it's the transition that represents a 1 or a 0, but we know from on this transmitter, a high value is a 1 and a low value is a 0. Since we are only watching at the time domain, we can actually replace the Qt GUI sync with a Qt GUI time sync, which only shows the time domain. So let's disable this block by right-clicking and choosing disable, and let's connect the Qt GUI time sync and selecting the right sampling rate. Let's press play. And now if we click with the middle mouse, a menu appears, and we can use this to stop the signal and watch the data. Let's stop when some data is shown, and you can see that it's a signal that goes from around -1 to around 1, but there is a lot of noise. You see that it is not a square wave. There is a lot of noise when the transition happens, and when it is a high value and a low value, you see that it oscillates a lot. But already we can see, for example, this is a 1, this is a 0, 0, this is a 1, a 0, this is probably 3 or 4 ones. So we are in the right direction. We need to remove a little bit of noise. To remove some noise, we could use another low-pass filter applied on the signal itself, on the data itself. We know that this signal is a 1200 baud, so that at most the frequency of this signal should be around 1200 Hz. Let's put a low-pass filter in between the quadratic mode and the Kotegu sync, and we will want to set the cutoff frequency to a little bit more than half of the baud rate. We can actually create a variable which we'll call it baud, and we know that the baud rate is 1200, so let's set the cutoff frequency to around half of the baud rate times 1.5. Transition width, it could be around 300 Hz. This value is mostly arbitrary for the transition width. So we see that the cutoff frequency arrives at around 900 Hz. Let's press play. And there is some problem with the signal. We actually set the wrong sampling rate, because the default is 2 MHz, but the sampling rate is actually divided by the decimation. So let's divide by DEC, and let's try again. Perfect. Now let's stop on our signal, and you can see now that the high and low transitions are very smooth and very clear. There is no more ringing. There is no more big oscillations on the values. Okay, it looks a lot better. One thing we want to do is make sure that the signal is centered around 0. You can see that it is not always the case, especially if we get the wrong frequency, then the signal will be not centered around 0. Let's for example change the frequency and see the effect. If we now press play and stop on our signal, we see that the signal is heavily shifted towards the one side. This means that we could get a 0 bit which is higher than 0, and this does not register as a 0 bit. To make sure that the signal is actually centered around 0, even if the frequency is slightly wrong, we can correct for the bias. This offset between the 0 value and the average is a bias in the signal. To correct this bias, we can use a DC blocker. What the DC blocker does, let's switch to float, is remove the bias from the signal by removing the average value. Let's try and stop on our signal. But you can see that now it doesn't look quite right. Sometimes the signal goes too close to 0. This is because we set the length of the DC blocker to 32, which is the default value, which means they will do the average of 32 samples. But we actually want to do the average over a long period of time, because this bias does not change with time. And 32 samples is too low. Let's try to put it to something like 10,000, which means we'll do the average of 10,000 and remove this average from the signal. Let's stop on the signal, if we can. And you can see this is more or less centered around 0. Let's fix the frequency anyway, just to make sure that we are centered. And let's see what else we can do to improve this signal. One thing that we notice is that this signal is not a square wave. It is actually very rounded. This could be actually a problem because we want to receive a square wave. But by cutting off higher frequency, we actually made it impossible for this to be a square wave. So we want to do some manipulation to make it be a square wave. There are other ways to achieve this, and I will try a simple one, which is to use a threshold block, an add constant block, and a multiply constant block, and you will see why in a second. Let's switch the types. The threshold block, if we open the documentation, it tells us that if the signal exceeds a value, it will output a 1 until the signal falls below another value. Then it outputs a 0. We can set it so if we set the low to 0 and the high to 0, when the signal is higher than 0, it will output a 1. When the signal is lower than 0, it will output a 0. So this will make any sample which is above 0 a 1, and any sample which is below 0 a 0. Then we actually get an output which goes from 0 to 1, but we want an output that goes between -1 and 1. This is because the processing that we will do later requires a signal which is 0 mean, so the average must be 0, and it must go from around -1 to around +1. So we will add a constant to the output of the threshold, and this constant will be -0.5. This means that the signal will go from the low value of the signal will go from 0 to -0.5, and 1 will go to 0.5. If we then multiply the signal by 2, we will get an output which goes between -1 and 1, which is what we want. Let's see the output of this. Let's stop on our signal. It is now harder to discern what is the signal and what is the noise, because all the signals are between -1 and 1. But anyway, you see that the signals are constrained to be either -1 or 1. Now the only thing that's left to do is to turn this into a bit stream. So we know, for example, let's say that this one is 1 bit and this one will likely be a 1, then the next bits will be probably 2 zeros, because you see the length of the signal is double the length of this one. So we'll need some way to transform this data to 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, etc. To do this, we'll need to use some synchronization method that we will see in the next lecture.
So that's all for lecture 7. We have arrived up to the demodulation of the dummy transmitter data. We will start from here during lecture 8 and arrive to the interpretation of data. We hope that you'll find this video useful for setting up the course with your students. We remind you that all the materials can be downloaded for free on the SDR Play website and at the link that you will find in the description of this video. Thank you very much for your attention, and see you soon for lecture 8 and the 4th video tutorial.